So this is the problem that we were discussing about, right? So design of a synchronous mod 6 counter using JK flip-flops. So here you can see that we have used Q0, Q1, Q2. From 0, 000, I want 010, then I want 011, then I want 110, then 101 and 001. So which means this is not in order, but I have given a random order here, and I want my circuit to function in this fashion. Okay, so once it reaches 001, I want it to reach 000. So what I will do is I will make a state diagram. Okay, I'll draw a state diagram, and I will first start with the initial state. Okay, so the initial state is my 000. So I will start with this state, and next it is going to 010 and then 011. Just like I will follow all of these. Okay, all of these I will put it in my state diagram, right? So you can see here after 001 it is 001, it is going to 000, right? Okay, so this state diagram is very important for us, because once we have this, it is easy for us to create the circuit excitation table. Okay, fine. So now have a look at the circuit excitation table. So before that, I have put here the excitation table of JK flip-flop, right? So once we have the excitation table of JK flip-flop, just for our easiness, okay, just for making things easy, okay, I have mentioned that we have these rows, okay, 0, 1, 2, and 3, okay, just for making things simple. So here, as you all know, we have to take Q2, Q1, Q0, okay, and this will be our normal order, okay, which means 0, 1, 2, 3, 4, 5, 6, 7. So this is our normal order, okay, and the next state, okay, so which means I have to every time refer to my state diagram. So after 0, after 000, I should write 010, okay, then after 001, so check for 001, it is 000, right? So that 000 will come here, okay. Similarly, check for this value 010. So for 010, for 010, it is 011. Okay, so that value will come here. Okay, so I think now you have understood, right, how we have got this table. Have you all understood? Yes. Can I have some response, please?
Yes, sir.
Okay, so ultimately we will even look at this 100. Okay, so just check, we do not have 100. Okay, so what I will do, I will just put a dash, which means there is nothing there. There is it's like a don't care, which means we do not have that kind of state. Similarly, we don't have a 111, right? So after 111 also it is all 3 dashes, okay, which means there is nothing. The next step is easy, as you all know, right? So we need to take a reference of the excitation table, and Q2 and Q2 star will be uh, taken into consideration. So it is just as good as Q and Q star, and this JK will be filled here. Okay, this JK is filled here. So ultimately, if it's 2, then I take J2, K2, then J1, K1, J0, K0. Okay, so for don't care, I have used a dash here. Okay, do not get confused. Okay, let's see, it is 0 and then 0. Okay, so for 0, what do we have here? 0 and don't care. Okay, so instead of don't care, what I have done here is I've used 0 and a dash. Okay, 0 and a dash. So ultimately, this is how we start filling J2, K2, J1, K1, and J0, K0. So once we have this table with us, it becomes easy for us to represent this using our K-map. So fill up these details in the K-map, okay? And these are the equations that you are going to obtain. J2, K2, J1, K1, J0, K0. Okay. So once we have these equations using K-map, then just check J2 what I'm doing. I'm giving Q1, Q0. Next, K2, I have rotated. Okay, I have rotated the flip-flop towards my anti-clockwise once. Okay, normally we used to have clock this side, but just for a change, I have kept it in this fashion so that you get used to these also. Okay, so that it's easy for us to represent the inputs at the bottom and outputs at the top. Okay, then your K2 is given Q bar, then J1 is given Q0 bar, then K1 is given Q2, and J0 is Q1, and K0 is Q2 bar. Okay. So this is how we represent things. Alternative representation of the, now this point is very much important. Okay, as I told you, we can even represent the same thing. Okay, using my D flip-flop, using my T flip-flop, using my SR flip-flop. It's not only that I am implementing this using JK flip-flop, anything can be used. Okay, fine. Anything can be used. Okay, so since here in our question, okay, in our question we do have using JK flip-flops, so I don't have an option, I have to use JK flip-flops. Okay, so this is how we design the counter. Now you can just refer to this general diagram. Okay, I have even given a general diagram here where JK and then C, the clock is common, and this is given to clock pulses. Then your outputs, okay, whatever outputs is actually given to your logical network, which means how it's going to perform. Okay, now when I say how it's going to perform, which means I am characterizing my circuit based on the next state. I am making my circuit go to, from 000, I'm making it go to 010. From 0, I'm making it go to 2. Right, so I am characterizing my circuit in such a way that it functions in this manner. Okay, so my outputs are actually given to the logical network. So this is just a general diagram for your reference. So any doubts, students, here? Any doubts here? Please ask. Do we have any doubts?
Sir, can you explain that implementation like in the cycle once again, along with the truth table?
Along with the truth table? You mean
Yes,
the
sir.
excitation table?
Yes, sir.
Okay. So as we discussed yesterday, okay, the same analogy is used here, right? So present state will have the normal count. Okay, it will go from 0, 1, 2, 3, 4, 5, 6, 7. Now till this part, all of you are clear? Please respond so that we can go quick.
Sir, I had a doubt in the fourth state, sir, like the state where the inputs are 100. Why is it dash, sir? Like there is no next state for that
Yeah, that's
input.
what, there is nothing. I've already explained the same, right? Can you find 100 here in this? Is there any
No.
100? Nothing,
No,
right?
sir.
So I do not know what state is it's going to happen. So what I'm doing, I'm giving a don't care, which means that state you don't consider at all. I'm
Okay.
telling my circuit don't consider 100 because I do not have it in my question, right? I have to use only those which are in my question. Now you see how many are there. Let us just keep marking. I have 000. Okay, then I have 010, and I have 011, and I have 110. Okay, then 101, right? So you can see only across those I have my next states. Yes or no? Wherever there is tick mark, you see? Yes or no? Only
Sir,
across
even
those.
001, no, sir.
Which one?
001.
001. I put the arrow here, no? Okay. So only across those I know what is going to be my next state. Others I don't know. Others like 100 is not here. 111 is also not in my state diagram. Right. So for those I will be giving as don't care. Any doubts here?
No, sir.
Okay. The next step is comparing Q2 and Q2 star. This one I think you all know, isn't it? Yes, or
sir.
no? Just take this column. Okay, think that there is only two columns now, Q2 and Q2 star. Okay, just compare these two. And these two you will have to compare with your excitation table of JK flip-flop. So I have a 0, 0 here. So 0, 0 means what? 0, don't care. So 0, don't care will come here. Okay. Then I have, let's take the other case. See here I have 1, don't care. I don't have that combination here. So my full thing is going to be a don't care. Okay. So you can see that, whichever combination I have here, 0, 0, 0, 1, 1, 0, 1, 1. Okay. I will be using only those. See, for example, 1, don't care. I don't have that state here. Do I have that state here? 1 and don't care? I don't have. So what I will be doing, I'll be giving it as total don't care. Understanding?
Yes, sir.
Yeah. Okay. So this is how you can actually get things done. Okay, when you are thinking of the designing of counter. Now, what I want you all to do is, I want you all to try and check. Okay, as to which uh, uh, whichever equations that we have got. Okay, is it proper or not? Okay, so you can put this into K-map, okay, and verify the equations that I have written here. Check if you are getting the same equations. Okay, so try and do that, and you will be able to understand it in a much better way. Okay, so with this, we actually conclude our fourth module, and we will be moving on to the next one. Okay, the next module, which is nothing but your last module. Okay, and that will be talking to us about a few more concepts, higher level concepts, where we will be talking of Mealy machines, more machines. Okay, and the sequential design. It talks about fully about sequential circuit design. Okay, more and Mealy models. Okay. So this is our model 5, which is sequential circuit design. And the first topic that we will be discussing is about Murray and Mealy machines. Okay. So we have seen this actually in our previous classes. Okay. Just that, we have to revisit them. Okay. Fine. So just have a look at this block diagram. Okay. And here you should be able to understand that if this is our input logic can be anything. Okay, a function, a random function, and then it has memory, and then the output logic. How they are connected is important. Now the input variables do have the representation as I. Okay, and your excitation is represented as E. Okay, and your clock is also given to your memory. Now you have something called state variables. Okay, so the output which comes from the memory is called your state variables. Now the output logic, okay, the output logic is given as O. Okay, the output logic is given as G and the output variables is given as O. The main thing that you have to know here is your input variables are connected to your output. Okay, input variables are connected to your output. So if this combination is present, okay, then we term it as Mealy sequential circuit model. Look at the other combination, okay, where the input, okay, is not connected to your output. So which means your output logic is only dependent on the output from the memory. But here it is also dependent from the input variables as well. The memory is also contributing to the output, and the input variables are also contributing to the output logic. So if input is involved with your output, then we call it as Mealy sequential circuit model. If there is no input contributing to your output logic, then we call it as your Murray sequential circuit model. Any doubts here?
So can you repeat once again?
Which part you didn't understand?
So the difference between the two models,
Yeah.
which you told just now, sir.
Inputs connected to output, then it is Mealy. When input is not connected to output, then it is Murray. Okay. So this dotted line is showing that there is no connection. I have written here. Okay. So there is no connection between the input and the output logic. So initially we will have just input logic. After to that, the output of input is given to the memory, and the memory's output is given to output logic. Here output logic also has the inputs from the input variable. So which means I am going to get my output with respect to state variables, okay, and also with respect to input variables, which is I. So I and S are both needed for the output logic. But here it is only dependent on the state variable, Okay, so the output of memory, part of the output memory is again connected back to your input. Even here, the same thing. Output memory is connected back to your input logic. Okay, so if your output logic is only dependent on your memory, then it is called as Murray. If it is dependent on input as well, which means if there is a connection from the input side, then it is called as Mealy sequential circuit model. Any doubts here? Any doubts here?
No, sir.
Okay.
No, sir.
Fine. Thank you. Right. So we develop notation and techniques for designing synchronous sequential machines. The two most prevalent sequential circuit models are Mealy and Murray models. So these two are the most used sequential circuit models. It involves combinational and memory subunits. Okay, so as I told you, how do I say combinational? Because it has memory block. Okay, sequential, do not have, sorry, combinational circuits. Okay, if there's a memory, okay, then we can call it as a sequential circuits, right? So the logic functions shown in the model diagrams translate input and flip-flop output information. So whatever information that you have here with the input and memory, that is passing to your output logic. The input logic produces the excitation inputs to the flip-flops. So whatever is your input logic, okay, that is creating something called excitation. Now we have seen excitation table, right? For JK flip-flop and for T flip-flop and all those things, right? So similarly, we will be referring to it as excitation, right? So input logic is giving us something called excitation. So this is referring to our excitation table of different flip-flops. Okay, right. A Mealy sequential circuit differs from Murray in the variables used to generate output. Satvika, you can stop doing that. Okay. Yeah. And so the only thing here you can remember is, okay, the sequential machines, okay, the input, as I mentioned you, there is no connection between the input variables and the output logic in Murray, but in Mealy there is a connection. In Mealy machine, the external input variables, okay, which is I, and the state variables are applied to the output logic to generate G, okay, and the output. Okay, so this is important. Okay, this definition that you are seeing here, if I ask what is a Mealy machine, then this is important. Okay, and a Murray machine, okay, that you can see here, okay, a Murray circuit is the output. Okay, so which means there is no connection, okay, between the input to the output logic. It is dependent only on what? Only on state variables. So the output is only dependent on state variables. This dotted line is just showing you that there's no connection. Okay, the reason why I have put it in the form of dotted line is just for you to differentiate, okay, between the Mealy and Murray. So which means there is no connection from the input side. Okay. Now we will have to learn few definitions, okay, as to what is a state diagram and all those things. Okay. Now since we have already implemented them, okay, it becomes easy for us to understand as to what a state diagram is. Can someone tell me what is a state diagram? We have seen, right, few state diagrams. So what is a state diagram? What information is it giving us?
A particular state in which it is, sir.
Yes, it gives us information in what state it is, what is its previous state, what is its present state, and what is its next state. So all these information is given to us, right? So state diagram is a pictorial representation of behavior of a sequential circuit. Okay? So figure shows a state diagram. The state is represented by a circle and transition between states is indicated by directed lines connecting the circles. Okay, so this is going to be my state representation, and this arrow is actually showing me that it is going from one state to the next state. Okay, so here you can see 0 by 0, 1 by 0. It means, okay, the numerator represents input and the denominator represents output. Okay, so it can move from one state to another state only if a particular condition is satisfied. Okay, so if in case you know the arrow is given in this fashion, okay, having the same loop, okay, then it is called the next state is same as the present state. Okay, so if it is moving from A to C, then I can say that it is going from one state to another state. Okay, if there is a loop, okay, if there is a loop here, okay, then we say that it is in the same state. It is in the same state. It has not moved from B to elsewhere, right? So numerator is input and denominator is output. Okay. So any doubts here? Have you understood this diagram? So the circle and transition between states is indicated by lines, directed lines connecting the circles. A directed line connecting a circle with itself indicates that the next state is same as the present state. Okay, like how we have here. If it is in the same, if the arrow is showing to the same circle, then it means even in the next state, it is in state A itself. The directed lines are labeled with two binary numbers separated by a slash. The input value that caused the state transition is labeled first, which means in the numerator, and the output value during the present state is labeled after the slash symbol. The one which is at the bottom is your output variable. Okay. So in Mealy model, okay, this is our Mealy model, which means I am giving input by output, and state is inside. Okay, this is my Mealy model. Now in my Moore model, it changes. Okay, so my inputs, okay, my inputs are just represented here. Instead, we had divided by output. So that divided by output goes into the circle, and we just say state A, and the output is at the denominator. So you should be able to differentiate the difference between Moore model and your Mealy model, right? So you can see here it is A by 0. Okay, but here it is not A by 0, it is only A. That 0 I am representing here, input by output, because your state transition is dependent on the input also, right? Input and output. Why is it so? Because we saw in the diagram, right? We saw in the diagram that our output is dependent on the input also. So input by output. So that is why what I am doing here is I have represented it as input by output. But here there is no connection, right? There is no connection in Moore model. There is no connection between our input variables. So input variables will stay outside, and the state transition is only dependent on the output, right? So this is my state representation, and the ones that you see here, okay, 1 0 1 0 0 1 0 1, all this are nothing but the inputs, which is the numerator in which model? In which model is it the numerator? Students,
Mealy's model.
yes, in Mealy's model, right? But here in Moore, I am not using numerator denominator concept. I am only giving my inputs at the outside, okay, and the denominator I am putting inside the circle. Okay, so this is my output of the state, input of the state, state representation. State representation is like state 1. For example, we saw 000, right? So that 000 can be state 1. Example, okay, right? So, this is about your state diagrams, okay? The differentiation between Moore model, the differentiation between Mealy model, okay? So try and revise these concepts, and in our next class, okay, I'll be taking up with the state table. Okay, now this is again another different concept where we try to extract data from the graph and we put it in the tabulation form. Okay, so this is your state table. So we will see another table called transition table, how it is done.
Sir, I had a doubt. Sir, in the Mealy's model state diagram, sir, like for the different states, sir, like A, B, C, D, why have they written 0 by 0 on the top, sir, for every state?
No, it is just to show that input also was 0, output is also 0. We will come to
for
it.
State A.
I will solve, yeah, I will solve that. Okay, I will solve these problems. This is just for you to understand how the graph looks. Okay, here you don't have to consider why is it 1, why is it 0. No, we are only naming the parts here. Understood? Naming the parts of the block diagram. Okay.
Yes, sir.
Yeah. So when we solve problems, then we can try and understand as to why is it 0, why is it 1. I will explain that. Right now, we are just having a look at how the graph looks. What are the parts of the graph? Okay, what is this called? Why is it like this? Okay, so just naming the graph and what are the contents of the graph. Okay, so once when we start solving problems, okay, I will show you as to how we actually get things worked out. Okay, so I'll be showing it step by step, how we consider, what kind of calculations we do, okay, and how we get the state diagram, how we get the state table. Okay, so all this we will be seeing with respect to problems. Okay, extensively we will be solving problems and we will try and understand. Okay, this is actually a very simple module. Majority it is concentrating on Murray and Mealy models. Okay, wherein you will have to develop state tables, transition tables, and develop circuits, construct circuits. Okay, and yeah, so we will have an extensive learning about all these concepts in our upcoming classes. Okay.